Hello, gentle readers. Welcome to another episode of Logos 2021st Century Foundations. This is Ross Finlayson. Today's April 12, 2025. It's about 12:30 in the afternoon here. A breezy day, a late spring, early summer sort of day. And today's consideration will be that previous conversation was about inverse contradiction after the end runaround bit, and helping to explain that the principle of contradiction, which is kind of held up as like one of the bases of reason, is better founded by a principle of inversion to arrive at a wider and fuller dialectic, just in case it would otherwise kind of rewind thousands of years of the usual philosophical foothold to make for these things. And that otherwise the entire kind of approach to the wider, fuller dialectic would be a bit frustrated by a principle of contradiction, which can't do yet more than vouch for a given development's internal non-contradiction. Yet that it's always possible to provide an opposite argument, which is just as strong or otherwise. Then that this principle of inversion was put up to more thoroughly, as it was put, to make for a principle of sufficient and thorough reason why that was so and kind of relevant then. So with that kind of figured out, then we might be able to kind of set aside the rhetoric of the logos, the discourse, to the rationality and the reason as what needs to be satisfied to have a way to be thoroughly correct in these matters, as having that kind of now a given. And so it's fair to say that it's no longer missing from what is so often simply absent from usual accounts that claim to offer foundations. So it's just a usual sort of thing that this knack about and turning things over and a wider, fuller dialectic makes for a better, more tesseract-like square of opposition to make for these things like the hypercube distance is one, what result reflections on the infinite and the vanishing, and as to why these superclassical notions still account as from their superclassical expositions, yet are put together in a way better altogether suited toward a kind of unified or holistic course of reason, rationality for what's natural and real. So that is that's something that I suppose it was about 25 or 30 years ago when trying to figure out from fundamental theory is what's the first axiom, and that's what was arrived at was inverse was the first axiom. And then here it arrives at it's not even so much an axiom as part of this axiomless natural deduction. So then the idea of axiomless natural deduction, it kind of goes hand in hand with this principle of sufficient reason, and then for the principle of perfection and so on. So we'd point out Leibniz for that and Hegel for that, and then also the usual various notions of duality and the reasons why things are infraconsistent vis-a-vis the consistent, which is so necessary to establish an altogether integral, a whole structural thing that is thoroughly structural and satisfies all its matters of relation and structure for constructivists. That we can be constructivists and formalists and intuitionists and thusly altogether be kind of more thoroughly satisfied for the surrounds. So here for foundations, there's like a foundations and an entire foundations. So what I thought to do today was look through these books a little bit that I've gathered and which ones I thought to read together. I wanted to look at this Noakes's A Textbook of Light. And so Noakes wrote this Textbook of Light and a bunch of other cool textbooks like 80 years ago or 100 years ago. When was this? This is G.R. Noakes's A Textbook of Light. And it was from the Aldenham School at some point in time. And he also wrote a textbook of heat and textbook of electricity and magnetism. But Noakes' textbook of light is really pretty great. And he starts with like what's usually given as the electromagnetic spectrum in a little fold out here. That G.R. Noakes, M.A., Oxon, F.Inst.P., from Cheltenham College, formerly senior science master at Giggleswick School. From this book from Macmillan and Co. in 1948. He has here the electromagnetic Hertzian waves from the long radio waves in the dry, which at 1500 meters. The medium radio waves are short radio waves as to like 1 wavelength in centimeters. That this scale is calibrated in centimeters. Radiation from oscillating electric circuit and the wavelength calculated from electrical constants of circuit. So this wavelength gets reflecting on whether sometimes wavelength means is with regards to light, it's kind of as with regards to the color it's connected, but with electromagnetic radiation, it's variously with about the intensity is with the wave packet and also about the wave velocity. So here it's kind of interesting that the natural unit then of the wavelength is this calculated from electrical constants of circuit. And then it gets up into the infrared, or rather down into the infrared, and then through the visible spectrum of red, orange, yellow, green, the greens, colorless green, blue, indigo, and the violets, and violet and purple and indigo with regards to the 3 ultraviolets and the 1 infrared. And with some particular empirical relations here about the 10,000 AUs, 1 mu, and at 10 to the negative third, the limit of infrared in the solar spectrum. And about the fluoro-optical and thermally, and about thermocouplers, bolometers, and fluoro-optical parts. And then within the visible spectrum, from red to violet, as it's noted. And here, when we're reading from Ryd, and then also from this a little bit about when Newton studied color, we're all familiar with Newton's spectrum as according to the prism. And then when there's discussion of the prismatic and chromatic and the dual tristimulus color space of color. That then there's also, after Newton, he kind of has these secondary spectrum up after the primary colors and blue and yellow and orange and green and this kind of thing as besides and also. So that just helps to affect or reflect that the model of light is sort of super classical again and of color, because in our tetrad of quantities with the kind of like as after the 4 nuclear elements of the atomic particles, the electron, proton, neutron, and photon, about usually the massy and protons as connected to the charged and the electron. Then for the neutron, in the neutron lifetime, and then light speed, one might aver to exchange the role of neutron and proton with regards to the massy and kinetic, as otherwise with regards to the charge and the electromagnetic. But it's about that tetrad of quantities, and then light be in particular about where it all just kind of comes loose and falls away, and this kind of thing. Then it gets up into X-rays, and gamma rays, and those with regards to the bombardment with electrons, and then ionizing gases, vis-a-vis soft X-rays, strongly absorbed by most substances, and hard X-rays, less so. And then as with regards to the gamma rays, which people say are not, that penetrate everything. The shortest gamma rays, most penetrating, emitted by thorium, the longest by polonium, and that occur with emission of an electron beta particle when the nucleus of a radioactive atom disintegrates. Gamma rays of wavelength greater than 10 to the 9th centimeter, indistinguishable from X-rays and diffracted by crystals. Those of shorter wavelengths studied by means of the photoelectric effect. This helps to show that then all this is what's called electromagnetic radiation. Is there's nuclear radiation kind of in the massy and kinetic, and then also about the gamma rays, and then in the X-rays and stuff. There, it's not electromagnetic really anymore. And it describes how the diffraction stops happening and these kinds of things with regard to light has diffractive character, and these other ones do not. And the electromagnetic has its own fluctuations in the electrical field. So with regards to radio, so the radioelectric and the radionuclear being different. And then also that otherwise that all this stuff is related by frequency and wavelength, or just by wavelength, vis-a-vis just by frequency. Then that wavelength and frequency being kind of reciprocals make for a product to result at a given quantized discrete amount of energy. That it's all related to this energy thing, but that one most model of fungible energy lives in 4 different fields according to 4 different forces and all the potential fields and these kinds of things. So this chart both helps explain and demonstrate that they can be kind of put in one map according to one legend, but then each of these other components, the descriptive and the empirical, describe why they're different. So all of these things are not like the other. So this textbook of light then starts, as first edition was 1937. It's said to be for sixth form students specializing in science. No attempt has been made to exceed the limits of the subject by dealing with points such as simple harmonic motion. That's kind of the idea of what is a wave and why do we call these waves at all, and then how do they relate in as waves as models of propagation in an open system. And the Rutherford Bohr atom, which receive adequate treatment in mechanics and chemistry. In some places, in explaining astigmatism and distortion, an illustrative method, calculus has been used throughout. Polarization, the ultraviolet and X-rays have been dealt with rather fully. And here throughout the book, brief accounts of modern applications, particularly in medicine, have been given. Many of the suggestions of the 1934 report of the Physical Society's Committee on the Teaching of Geometrical Optics have been incorporated. So yeah, the optics in regards to the sources and imaging and the virtual images and these kinds of things and focus, and those being almost always entirely contrived as, through a telescopic tube that's perfectly round and according to these lenses that are perfectly lens-like in a sense of being, according to the parabolic and hyperbolic, exactly making points of focuses that are well understood and unique and singular in these kinds of things. Makes for that there, as we kind of covered a bit in the discussions of waves in layers and diffraction and the impedance, and then the idea of whether a reflection was a geometrical reflection, that the angle of incidence was congruent on both sides, or as with regards to whether it's optical and where diffraction happens, where the phenomena of refringence and refraction after diffraction happen, which don't in all electromagnetic waves, but do mostly about whether it's optical like in character, whether it's light like in character. Have that these are the kinds of the things that are explored variously, and there's things in their own empirical fields that then in the education given up to them is given like, this is the creaky apparatus, this scaffold in the middle that these things can be attached to variously. They would pull each other down. They don't match in the edge and corner cases, but at least then it gives a pretty strong theory getting into the adiabatic and for linear Wheat charts, so then we can make electrical engineers out of everybody, because the mechanical engineers are going to go their own way into tribology and rheology, and the opticians, of course, is just kind of underdeveloped field. And then as regards to antennas and the radio electric, that's its own kind of thing as well. So this just goes to show that then the course is kind of like to get people up to having the common language of science, because it's not sure yet where they would actually be able to go in school and to figure out what they could do in terms of being able to be given resources and apply that and result value. So according to this engineering case kind of. So it says, and then he's got some exercises. He talks about the standard advanced treatises. Much of the material on photometry and ultraviolet spectrographs is from literature kindly supplied by General Electric and Adam Hilger. Many firms and individuals, Tarrant says, in the preface of the second edition, is 4 pages on Bohr's calculation of the Balmer series wavelengths have been added. So Balmer is in the spectroscopy. And so you got like Balmer lines and Zeeman lines, but then you got like Lyman alpha and these other things about the second spectrum variously, and then also about spectroscopy and spectrumoscopy, or as it well may be, not to coin a word that would just be useless, but that the spectroscopy is dealing with the aspects of the continuous nature of the spectrum and the discretization of it and the quantization of it. Largely it's built after the hydrogen line, but when it's arrived at the sodium has at least 3 lines, then that helps to affect or reflect that besides the usual central principal branch, it's a multiplicity theory with regards to these. For something like Reynolds numbers or something like that in the fluid, and everything kind of has a fluid model. Then about what that means when these different empirical milieus are in effect. Of course, whenever you hear the word effect in physics, it usually means something that demands its own little theory because the greater theory does not account for it. And so if you look up something like a list of effects, then you'll find all kinds of effects, like the Hall effect, the quantum Hall effect, 2 different things, or the thermocouple, as after Seebeck and Peltier effects, now called junctions and explained by continuity laws between them, and the Compton effect, Cherenkov, Coriolis effect. There's all these different effects, and what they indicate is where the empirical milieux and the dynamics, which start within a couple orders of magnitude of most states of dynamism or rapid change, or coupling forces and of coupling, or dynamism, or fixedness of a sense. The effects are that's what they're so called. Then it has the chart of wavelengths we just looked at, and then the reflection at plane surfaces. That's the geometric, and then into curved mirrors, and the idea about how to apply that each of the image rolls over as it gets reflected. And so when we talk about Fresnel stuff, then with the large lensing, is the idea is like, well, we kind of got an idea how light goes. It goes just straight as an image and expands spherically. And then there's also kind of unidirectional light is with the coherent light, as it's called, like the light amplified by the stimulated emission and radiation, or lasers, invented sometime after masers, the microwaves amplified by the stimulated emission and radiation. And so with the unidirectional and the omnidirectional. Then there's also the idea about the imaging, that light is massless, yet it still has some kind of energy in it. And these are real photons, then, in that sense, and the wave packets, insofar as in there in waves all the time, wave-particle duality, of course. That it goes to show that then in the light diffraction and refraction, and after reflection, which is geometrical, that this other stuff is optical. Then is with regards to how that is and how that so could be. Talks about thin lenses and measurements and problems of lenses, defects of lenses, the camera and projection lantern, the eye, optical instruments, wave theory, velocity of light, spectra, the spectrometer, and color. Here's is discussed. There's a dual tristimulus color space, as after a colorless green. Interference, diffraction, polarization, ultraviolet, infrared, and X-rays. And so, if that's chapter 20, I imagine take a look at that. And as I've been leafing through this book, it's got plenty of stuff, and a lot of it you'd find in, or the introductions you'd find in just usual courses about virtual images and imaging. But again, and then stuff like Beer's law, and as with regards to refractive indexes and the diffraction, a fraction of differences, a diffraction. That when I kind of figured out that a diffraction meant, as according to a formulaic approach, like a difference or a fraction or ratio of differences in 4 terms, a minus b over c minus d. and then that's kind of all it really boils down to. Then and then the refraction is as if about that coming around, and also with polarization, and then the refringence gets into the interference of that as it kind of wraps up inside of it. That this was kind of pleasing. It says if mu minus 1 over density is constant, and the absolute refractive index for air at 1 atmosphere pressure is is 1.00028, or say 1.0003. The value for air at 11 atmospheres could be . So this could help explain something like mirage, when the density kind of varies or becomes dynamic with regards to heat bubbles and magmas in the convection of heat, with regards to the adiabatic and non-adiabatic. They're explaining how mirages form and what they look like. And everybody's seen a mirage on any kind of hot surface through air. And that it's a matter of diffraction in this case. It could be derived from diffraction. And according to here, that density is given as a term, but when it starts to become one of these x squared plus minus 1 bits and a difference, it fulfills the same kind of thing. Starts keeping that kind of stuff simple. Limiting angle of a prism, the critical angle, what angles that have critical angle transmission, whether through or according to a mirrored surface, what reflects and what transmits. And here that was discussed with regards to like smart roof tiles that are passive cooling or passive heating, according to given manufacturing parameters, and understanding or knowledge of usual angles of the sunlight. Wollaston's method for refractive index measurements. And then he describes various configurations of experiment as with regards to the energies of experiment, which are inherent in the light rays. The total reflection and the partial reflection, a pulfric refractometer, glass prisms, the ray PQ, minimum deviation, advantage of using prisms. And this gets into things like analog computers vis-a-vis triangulation and this kind of thing according to the behavior of light, vis-a-vis the multiple perspectives. And then getting into this is thoroughly a textbook in the establishment of the setups and the ansatz of given geometrical configurations, or the configuration energy experiment. It talks about the rainbow, the primary bow, and the secondary bow. The inner and outer subtends an angle about 41 and of about 53. Both show the colors of an impure spectrum. The primary bow having its inner edge violet and outer edge red, while the orders of the color are reversed in the secondary bow. Other bows are sometimes observed near the inner edge of the primary bow and the outer edge of the secondary bow. The nature of these supernumerary bows, depending on the size of the raindrops. The region of the sky within the primary bow and just outside the secondary bow is always appreciably brighter than the rest of the sky, while the space between them is darker. The secondary bow is much less intense than the primary bow. And so it's about with respect to the size of the drops, and so here when there was Red Boyer's the theory of the rainbow. This kind of follows as after that, and so that's good to know that it's included here in Noakes' textbook, because when I read this, it was pretty thoroughly modern and up to date in a lot of these different kinds of things. The value of d diameter over di with the two internal reflections is small in the neighborhood of the minimum value of d, and thus for each color, the direction of minimum deviation will be that of greatest intensity. So this then speaks also to intensity and what that means when that's just like considered as like, oh, there's more photons vis-a-vis that actually is a ray of light or as a state of the transmission or propagation of light, that it's a large wave. in this area is with regards to amplitudes in intensity. And then intensity is also a product of over time. It's extended as well. So that and as to the supernumerary bows, these are similar in nature to the colored bands observed when a distant source of light is viewed through a series of narrow slits. So this is just from reading the Rude's Modern Chromatics about the polarizing goggles, or here that was a glacier goggles of sorts, and the idea of that these provide optical effects. These bands, which depend on the width of the slits and their distance apart, are discussed in the chapter on diffraction. So maybe diffraction is where we might look vis-a-vis the ultraviolet and infrared. So diffraction starts on page 281 in chapter 18. And what it says is, after reflecting telescopes and reflection at spherical surfaces, after line spectra, the Rydberg constant, the series relationship was worked out for the lines of the visible spectrum of hydrogen by Balmer, wavelengths of which can be written in the form 1 over lambda equals r times this quantity 1 over 2 squared minus 1 over k squared, where k equals 3, 4, 5, 6 for the 4 visible lines, and r is a constant called the Rydberg constant. Other series for hydrogen expressible in similar forms are the ultraviolet Lyman series, given by 1 over lambda equals r times 1 over 1 squared minus 1 over k squared, and the infrared Paschen series. 1 over lambda equals r equals 1 over 3 squared minus 1 over k squared, k being 2, 3, dot, dot, dot in the first case, and 4, 5, 6 in the second, and r the same constant. The limit of each series in the short wave side will correspond to the transition in which an electron has fallen to the E0 orbit from outside the atom. This is according to electron physics. Theory enables the energy corresponding to the series limit to be calculated. For example, in the case of mercury, it corresponds to the work done in moving an electron through 10 to the 39 volts. The ionization potential, or the potential difference through which an electron must fall in order to ionize an atom by collision, that is given the atom potential energy by removing an electron from its normal orbit to outside the atom, so put it in a state in which it is ready to emit the series limit line, was shown by direct electrical methods, author having marked that in italics, to be 10 to 39 volts for mercury. The energy corresponding to the emission of individual lines can also be calculated. The ultraviolet mercury line of wavelength 2537 angstroms units, I guess, needs for its emission energy equal to that possessed by an electron that has fallen through 4 to the 9 volts. I imagine that's that the author uses variously an exponent and a product rule. Direct experiments show that electrons which have fallen through this potential difference lose all their energy when they collide with mercury atoms, giving the atoms just the right amount of energy to produce a line. And that the 2537 angstroms line is then emitted. The single line thus excited is called a resonance line, and the potential difference through which an electron must fall to excite its resonance potential. So this speaks to that these discrete elements are just kind of the crests of the resonances which build up. And so that says that resonance theory is pretty great, and that these kind of aspects of the features of it actually really very well depend on those being discrete elements. The result, again, they're actually the result of resonance physics, and so they're not the particles, they're bigger than the waves. They're the resonances again, and those are just the kind of the crests of that as a wave. So resonance potentials and resonance lines. Then he starts getting to talk about the Stark effect and the Zeeman effect. Observations with instruments of exceptionally high resolving power show that single spectral lines are split up into groups when the source is in a strong electrostatic field, Stark effect, and strong magnetic field, Zeeman effect. This latter affording the astronomer a means of measuring the magnetic fields in stellar bodies. If the atom emitting light is moving relatively to the observer in the line of sight, the Doppler effect changes the observed frequency of the lines, altering their positions in the spectrum. And that's always going to be the case. But the Stark and Zeeman effects are particulars. Ordinary molecular velocities in flames and discharge tubes suffice to give the lines a finite breadth from this cause, and the motion of stars and rotation of planets give displacements which enable these motions to be measured spectroscopically. There's also the hydrogen lines are kind of visible through the cosmic dust, and that's what makes for standard candles and these kinds of ideas with regards to the sky survey and the use of spectroscopy, and then as regards to the mass spectrometer and those being kind of, as described here as via two different kind of approaches as to why they kind of arrived at then for that these formulas of Lyman, Paschen, and Balmer can deal with them in various ways, which are kind of like diffractions, but instead they're differences, because the diffraction is kind of like, well, it's you take a fraction of these two differences, but the spectral lines are differences of two fractions, and in fact they're just inverse squares, so kind of inverse square differences. The Balmer, Lyman, and Paschen series is. And then Bohr calculated the wavelengths. According to the Rutherford-Bohr picture, the atoms of all elements consist of positively charged nuclei surrounded by a planetary system of electrons. And so here one of the other books here is about nuclear theory, and it gets into like nucleons and what is in the nucleus and this kind of thing with regards to the isotopes, and that being pretty much linear as with regards to the periodic table elements, and that being not quite so linear. In the normal atom, the nuclear charge just balances the sum of charges of the electrons. That's in terms of the area, because atoms are assumed to have a given mass, and then a mole of them kind of occupies a given amount of energy altogether in a uniform way. As regards to ions and solutions and gases, is when, and then with regards to the densities, that otherwise though it just goes so that just balances the sum like for an area according to Gauss-Bonnet, or how the electron holes flow for current and these kinds of things. The simplest atom, and thusly our atomic theory that's based upon the idea that it's stoichiometric all the way down, is that of hydrogen, which has only one electron, and the mass of the nucleus is about 1,800 times that of the electron, so that it can be regarded as a fixed center. The simplest orbit is a circle. Here there's also that, well, all orbits, according to this inverse square kind of approach, are elliptical in practice, and in fact they're somehow different from that. But that the simplest orbit is a circle is when the center is infinitely greater than the outer, but yet the outer has enough velocity to keep moving. That's why, according classically, they would just collapse. That instead they just kind of reach this balance between the massy and the charged. Why the atomic model doesn't collapse? As with regards to that things like the real wave idea does collapse all the time, whereas the atom in its combined mass and charge model never collapses until you get to the nuclear with things like radiation and so on. Dynamics effects. The ordinary mechanics and electricity on which the following calculation is based may well be within the reach of the student, who is advised to refresh his memory by looking up the formulae and mechanics for the behavior of a particle describing a circle, and also the law of inverse squares and the meaning of potential in electrostatics. So that's something we're going to look at a little bit here in one of these other books. So that was kind of about the spectroscopy, and then he gets into about the Rydberg constant that's present in the spectroscopic series, about their final orbits, and the final orbit that go to variously Balmer's, Lyman's, or Paschen's, and in 4 and 5 corresponding to also other known infrared series. And then he says the general case of the inverse square orbit is an ellipse. While the shape of the orbit need not affect the result of the previous calculation, it can be used to explain the slight differences in wavelength of the many fine lines of which a single line is really composed. It's fine structure. So this helps to go to show that, yeah, spectroscopy is this resonance, and so it's all these other ones, all these fundamental tones, as they may be called, or as they are, which make this kind of overtone, which results having something, according to say, which are seen with spectroscopes of very high resolving power, and also explains the Zeeman effect. And the Zeeman effect is kind of like, well, that's Faraday's kind of, and as with regards to then this formula, which is a difference of two inverse squares, according to that being is for an infinite series, is kind of what got him his Nobel Prize, Zeeman there. In the unexcited hydrogen atom, the electron occupies the orbit, n equals 1. And then, so this doesn't so much get into the different kind of species of orbitals, or, what, I don't really recall them, S and D and P, the orbitals, the shapes and how many fill them up. It's just kind of just like we're starting with hydrogen, and because that's the most available thing. And then also, furthermore, we're starting just with these numbers, the most simple things. Well, with a heavy element, visible radiation is produced by the outer electrons, while the counterparts of the Lyman and Balmer series involving n equals 1 and 2 orbits, as the final ones are the K series and L series X-ray spectra. If n is the atomic number, the nuclear charge is n sub e, a calculation of the wavelengths of the lines, assuming everything be as simple as in the hydrogen atom, except for the increased nuclear charge, gives 1 over lambda equals this 2 pi squared me to the 4th over ch cubed n squared. This quantity 1 over 1 squared minus 1 over k squared, like the Lyman series, and similarly as for the Balmer series, adding this factor in the front of it, 2 pi squared me 4th over ch cubed, this and atomic number squared. For the K series and L series, for each series, 1 over lambda is approximately in the order of n squared, or the square root of the frequency is proportional to n. See if Moseley's result. So that probably explains what makes for the facility of the mass spectroscopy. Newer ideas have been added to the simple picture. Experiments have shown that electrons are diffracted like waves. And light wave calculations tell us all we need about the distribution energy, but the energy itself appears in quanta. The new wave theory of matter, called quantum mechanics, originated by de Broglie in 1924 and developed by Heisenberg, Schrödinger, and Dirac, used to calculate the distribution of electrons, which, when encountered individually, appears charged corpuscles. This enables a mathematical explanation of Bohr's quantum assumptions to be given and also deals satisfactorily with the more complicated atoms. And so the electrons are diffracted like waves. Isn't so kind of as with regards to the light and with the electrons in current are do not move far from their atom. They do not flow along the wire. It's electron holes is the idea. See, so the radiation of the electromagnetic radiation that's with regards to my earlier comment by diffraction, that I wouldn't want to go without passing, has that, though it's kind of demonstrated diffraction from electron beams, then there's this other stuff that is not so related to it. And so that kind of comes in and out of the picture of the electromagnetic radiation with regards to diffraction and the light-like character of diffraction. For further discussion of spectral theory, reference should be made to one of the standard textbooks on atomic physics. All right then. Fraunhofer lines, Kirchhoff, Fraunhofer lines, Kirchhoff and Bunsen. Fraunhofer, Cornu. Fluorescence, and then this gets in other forms of the emission of light beyond incandescence and fluorescence and these other ideas. And then color, this kind of reflecting on the color. The patch of light, when the red portion is cut out at A, the patch at B appears a marina green. This blue-green is clearly white light minus red, and the two colors, red and this blue-green, which combine together and give white, are called complementary colors. So this marina green would have to be investigated as part of the ideas of the colorless green. With regards to the chromatics and the prismatics, why that results kind of an additive color or a subtractive color and these kinds of things. Then he talks about primary colors, about intensity or brightness and hue, and the wavelengths, the primary colors, color triangle, and then we have our tristimulus color space, and the theory is of above and after that, about reflection and absorption, filters and pigments as those being different, ultraviolet and infrared. So then chapter 20, so chapter 19 is about interference and the famous experiment of particle wave duality as instantaneous in its observation. Interference pattern with regards to the angles and the distances and the rings. The Arago spot is a great thing. It's like, well, when you shine a light something and it has a shadow, in the center of the shadow there is a dot of light. There's a spot of light. It's called the Arago spot, and it's one of the most remarkable things to help show the superclassical nature of light, that it goes around is for a focus, and it helps to make for things like that it couldn't be according to the geodesy, and it's, I mean, it's not focused because it's occlusion, except it is focused by occlusion. So this larger Fresnel effect must be able to be shown if it exists in the sky survey according to telescopes, and more and beyond what shows up from like Einstein cross and Einstein ring, which is given that light behaves just according to the geodesy or what gravity says. That it instead is like, well, Fresnel says that it would start to lens just by being sufficiently large, and if you dig a well deep enough and put somebody at the bottom, they can see the stars straight up, and all the sun's light is blocked, but they can still see the stars light coming through. And then when you put a block between the light and make a shadow, then center of the shadow there's a dot of light, the Arago spot. So these all show that Fresnel lensing and large Fresnel, or Fresnel large lensing, are things to go along with Arago spot, and help explain that is like so, and helps explain why special relativity doesn't necessarily govern the light like, except insofar as it does for the classical partial accounts. Spherical wavefront. The case of a spherical wave diverging from a point source and falling in either a spherical optical or a circular aperture can also be treated simply. And then he talks about the fringes. The Fresnel calculation shows that the effect at the center of the shadow will be that due to half the amplitude of the first zone received. Zone plates, photographing the drawing on a glass plate, do actually act as lenses in this way. Whereas there's only one focus for a lens, there will be others for the zone plate. The points for which a blackened ring is cut out 3, 5, ... zones at a time instead of only one. So that gets into these ideas of the lensing, and then also the ideas of the second and higher spectrums of the emission, and the other spectrums of the absorption, and there's various notions that go on in the thing. So Noakes' textbook of light helps to introduce a bunch of different things at once, and is bringing together a lot of these different terms and help explain why they do stand up each a piece. Then for pulling them apart is something else. But usually when you see introductory textbooks, they don't really give much in the way of alternative things. They'll just like define adiabatic and then not define non-adiabatic. And then hopefully later it'll just come as part of the linear curriculum later. But these are kind of things it may well help to be arrived at this. Like at some point in time, we're not just given things that are branchless, but as soon as we introduce anything that has a branch, about the necessity to introduce both branches, because otherwise later half the people in the linear curriculum will be able to say, well, I'm just adding on another branch, whereas the other half will be is like, well, I never bothered to put that in my consideration when I started, and now I can't. And so that just gets into reasoning why the expositions of the superclassical accounts should have pretty much come first, so that then everything else after that is kind of easy. Sodium light. This is something about sodium light. But it doesn't mention much about, except it gives only 2 or 3 maxima of a glass plate with a diamond. So this is in resolving power, dispersive power, spectrum produced by gratings, optical instruments, and that the resolving power is the wavelength of light used over the relative aperture of the objective. Spectroscopes, Michelson's echelon. So both dispersion and resolving power are proportional to n, the order of the spectrum. I was looking at a device over here. It's called a clinometer, and it has an optical effect. It's not quite a grating. It just has a split in the middle, and then it has like a block in the middle. But as you look on two sides and like twist it back and forth a little bit and dial it up and down a little bit, it rotates and curves around the optics, and it's just a square telescopic thing called a clinometer, but it's got these effects built into it that provide these an analog computer of sorts. Michelson's echelon. With ordinary gratings, higher order spectra are faint. Michelson designed a grating which would produce bright spectra of very high orders, with many plates in them. So chapter 19 is polarization, and that gets into regards that as waves propagate, it emits waves. This is Huygens' principle. Huygens constructions, further incidences, sin A over sin R, the rhombus cut. Optic axis parallel to face of the crystal and perpendicular to the plane of incidence, both laws are obeyed. But otherwise, they're not. According to Huygens, the wave propagated in a uniaxial crystal consists of two surfaces, one within the other. Interference, ultraviolet spectrographs, X-ray spectrometers, biological effects. So this is in photomicrography. What is that word? Photomicrography. The compound microscope can be used to project a real image on the slide of a screen. After talking about the visual and photographic spectra. So this helps to show that the optical light is special with regards to the visual and photographic. And about something like 1,000, a wavelength 1,000 can be photographed in vacuum only. The difficulty was overcome by Schumann, who devised a method of holding the sensitive grains to the plate with a minimum of gelatine and the Ilford Q ultraviolet plate. The sensitive grains are on the surface of the gelatin. And this in the chapter, the ultraviolet, the infrared, and X-rays. Eye is sensitive to radiation of wavelengths between about 4,000 angstroms and 7,500 angstroms, the violet and red ends of the spectrum, respectively. Ultraviolet affects a photographic plate. Glasses are practically opaque below 3,000 angstroms, with the exception of the Gina uveole, which transmits down to 2,800 angstroms. Quartz is transparent down to 1,850 angstroms, and modern fused quartz is highly transparent at this wavelength and probably considerably beyond it. Fluorite is transparent down to 1,200 angstroms. That otherwise, these sorts of radiations is absorbed by everything. Fluorescence, phosphorescence, incandescence. Gamma rays, the products of the disintegration of the nucleus of a radioactive atom. Well, so Noakes has got a great book on this theory of light. This is the textbook of light. And it's something that helps to fill more of a theory that needs to involve the light-like in its composite elements that describe the color, and as well that being just one particular qualitative aspect, according to all these different kinds of configurations of detector and this kind of thing, that the other thing that's going on that's all called electromagnetic radiation, just because it propagates according to the geometric first, and then that being kind of like Cartesian, and then also that being Galilean, and then with regards to that being Lorentzian, and with energy going anywhere, and with regards to whether the components involved are Massey all, or they interact with the Massey all, or the charge or electrical, has that there are at least these things going on. But the textbook of light there helps to outlay the course about how things are built up, that we can at least determine some things and make good lenses, but at the same time mentioning there are things that where they fall apart, and that things that are considered to be like individuals or unique in spectroscopy are actually after these resonances in their derivation. And then also for things like Arago and Fresnel and a large lensing, and these that and Michelson, who's more well known for the Michelson-Morley interferometer than he is here for these arrangements of plates, which show these super classical things, or of higher orders of multiplicity. Say that Noakes' book is great, and so when I found that, I thought it was pretty good. Malchev's, M-A-L''CEV, Malchev's The Meta-Mathematics of Algebraic Systems. So this book I got, and I've looked at it a bit, and what it's about, it's a great book on algebra. And so I kind of put it together. This is from North Holland Publishers in 1971. To the Many Miles on the Volga in a Single Rowboat, from Reminiscence of P.S. Alexandrov. He says, almost half of Soviet mathematician Anatoly Ivanovich Malchev's published research contributes to the meta-mathematics of algebraic systems, or employs its techniques to obtain algebraic results. So, algebras, partial algebras, models, relational structures. Briefly, in algebra includes, belongs to, if and only if. Malchev most frequently uses first-order predicate logic, but propositional calculus and second-order predicate logic also occur. Formulas, sentence, and axioms. Similarity, type, and signature. The class of algebraic systems is abstract, closed under isomorphism most of the time, usually explicitly, but sometimes not. It is always consists of algebras of the same similarity type. The closely related notions of similarity, type, and signature present a methodological, if not conceptual, difficulty. Roughly speaking, the former specifies the number of basic operations, partial operations, predicates, and distinguished elements in an algebraic system, and the rank number of arguments of each. Signature specifies the symbols of matching rank used to designate these mathematical objects and logical constants. So this goes to help show he's developing a sort of the structure of algebras to help kind of figure out what they are and figure them out. Operations and with regards to things like the operator calculus, for things like arithmetic, which have defined operations, then into algebra, with regards to function theory, defining the relations between them, all these kinds of things. Classes of models with an operation of generation, defining relations in categories. Certain classes, model correspondences, constructive algebras, elementary properties of linear groups, closely related models and recursively perfect algebras, axiomatizable classes of locally free algebras, iterative algebras and post varieties, post being a proper name, Emile, I think it was, Emile Post, I don't know for sure, post varieties, universally axiomatizable subclasses of locally finite classes of models. So this gets into then what would be the kind of the higher order things. And so this is something to look at some more later. We spent a lot of time on Noakes today, but that's good because it helped to introduce and explore a lot of the concepts. This is Graustein's higher geometry, Introduction to Higher Geometry. When we think of the two given conics as line conics, a similar argument leads to the dual theorem. Theorem 1a is the singular points of the degenerate conics of the pencil of point conics determined by two non-degenerate conics have the same polars with respect to two conics and now are the only points with this property. And the dual says the only lines which have the same poles with respect to two non-degenerate conics are the singular lines of the degenerate conics of the pencil of line conics determined by the two conics. And then he says, it is clear that the singular lines of the second theorem are the polars of the singular points of the first, and vice versa. For if a point P has the same polar L with respect to both conics, the line L has the same pole with respect to them both, and this pole is P. So that's kind of nice, because a lot of the things that come up in this higher geometry are the duals, and helping to show that what's a singular and asymptote in one and unreachable by any matter of inductive analysis can be shown to have exist in the geometry, in the world of geometry, a place where it goes, and then to make for a way to build the completions and the analyticity between them, and otherwise that is kind of nice and like so. So and this is Sachs on nuclear theory, and so when we talk about atomic theory and nuclear theory, then this is kind of like where the nuclear theory is about the nucleons and their interactions as with regards to the hadron physics and what results like bosons, and the Quarkian physics is an entirely different approach, but they're both approaches, and so that's more about the electro weak, and this is more about the strong nuclear, in a sense, the nucleons, because the hadron physics gives like the asymptotic freedom to the strong nuclear force, but then makes up its supersymmetry in the electro weak force, or is with regards to the Higgs boson and then like a tevatron, or according to the billions and billions of electron volts. That helps to show that the tetrad of quantities is kind of in effect, vis-a-vis the usual derivations that have. We start with the Massian kinetic, and then trying to figure out how that all relates to the thing. And this is much more thoroughly explored in O.W. Richardson's Electron Theory of Matter, Cambridge Physical Series. The kinetic theory of electronic conduction. So usually we have that our theory of electrical conduction is after potential and linear Weichart and Compton, and that what Richardson seems to be describing here as a kinetic theory of matter, because this book is called The Electron Theory of Matter. So let's see what he has to say about that. He talks about the total energy and volume being a constant. Its physical state will nevertheless in general change with lapse of time. And that's about any relation. It means that in electromagnetic that it could achieve a resonance, or it'll achieve whatever matters of equilibrium, make for a constant in current or circuits. And then with regards to like a permanent magnet or something like that, it's to explain how a permanent magnet could be a thing, which is kind of that is like, well, it was molten, it was dynamic at some point, and when it reached its a state of being frozen, like that it reached a solid state, then the magnetic current lines were still kind of held in opposition. It becomes a permanent magnet. That these are the kinds of things that can help explain why then that's kinetic, because it's electromagnetic is always kind of kinetic, and if it doesn't really interact with anything, then it's just kind of the field, and it's according to Maxwell's variously E cross B or D cross H, one of which is defined, the other derived, but it could be either. And then for the greater lettered fields of electromagnetism as theories. That this is kind of nice though. Richardson is getting into a little bit more about and he's talking about the entropy and about the second law of thermodynamics. Final state is only steady as regards quantities, which are usually taken to be sufficient to describe the behavior of matter in bulk. And then he's talking about if we could find the motions of the individual molecules, there's every reason to believe the system would be found to be seat of very lively, never ceasing changes. And that kind of is called like activation energies, but it's really potentials. And so that's various different kinds of things. On the average, however, and actually the system contains an indefinitely large number of molecules. The distribution of the molecules in space and of momentum and velocity among the molecules is definite. Well, then we have to get into what momentum means. And he talks about genes. For Rayleigh genes has shown that in the statistically steady state, which is independent of the time, the most probable distribution is infinitely probable compared with the others. so that if we can find the most probable distribution, we shall have obtained the actual distribution for all practical purposes. So that helps to illustrate that Jeans set up a deduction saying, hey, if you can figure out for a law of large numbers how it arrives at this like this and so in the bulk, then it works out this like so. Boltzmann pointed out the intimate connection between probability of a given staticist and the entropy of the system. So Boltzmann here, we talked about taking out a Boltzmann's constant, the Molar gas constant. And that was something that deserves a little bit more discussion and deliberation, and taking what's a mathematical constant out of what's an empirical and physical constant, or figuring out where it's actually derived to be like so. To discover a fundamental physical constant in nature, which kind of should end up being none. And but as well gets related about 0, 1, and infinity. So anyways, these are some of the books that kind of go together in this theme. And this is Great Dialogues of Plato and Dante Alighieri's The Divine Comedy, the Inferno, the Purgatorio, and the Paradiso. Something for another time. Well, have a great day, gentle readers. Fellow Earthlings. Logos 2000. Light.